in energy, lecture number 11. So let's start, students. The chapter name is Work, Power, Energy, right? So before we go into the details of work, power, and energy, let's discuss about energy. Now, what is meant by energy store, right? So energy store means it's a property of energy, and it is something an object stores, or it can be transferred, right? So the important thing is, how does it transfer, right? So it can be transferred to perform a certain work, or it also there to heat up the things, So energy can be given, or it has a unit named as joules, because work done and energy got the same unit, joules. Now, to discuss this energy store and all that, we need to know what is meant by system. Now, remember that system means something under observation. If anything is under observation, we called it a system, or you can say an object or a group of objects, right? Now, system can be of two types actually. One is called as open system, and the other one is called as closed system. Now, remember that when you're saying open system and closed system, what does it mean? We suppose that, for example, you have a certain cup of tea, right? And it is placed somewhere which is open, like it's an open surrounding is there. The surrounding can be the environment. Surrounding is environment. So in that system, energy can be going outside and energy can be given from outside. Plus, mass can be given from outside and mass can be taken from outside. That kind of system in which you can place anything into that energy and mass, and energy or mass can be taken out from the system. That kind of system is called as open system. Now, what is meant by closed system? Closed system is called as isolated system. Now, if you perform something in an isolation, same cup of tea, but you're placed somewhere where the energy which is coming out of it will be actually within an isolated region, right? Where energy, neither a mass nor an energy will be transferable or coming into the cup, you call that system as a closed system. So there are different type of systems we have it. Now, there is one more thing. When a system is in equilibrium, nothing changes, so nothing happens. When there is a change to a system, energy transfer. Like, for example, if you placed a cup of tea, fine, it's okay. But if, for example, I'm giving you an example, then you will understand it. Let's suppose you bring a cup of tea here and its temperature is 70 degrees Celsius. Where you bring it in a room, the temperature is 35 degrees Celsius, the room temperature. Now, as soon as you bring that cup of tea in a room, the temperature starts falling, right? It will keep falling. It means that energy is being transferred from the cup to the surrounding, which is a room, right? Consider it as an isolated or a closed system. Now, energy will be keep transmitting or transferred to the surrounding until the 70 degrees Celsius temperature reduced to 35 degrees Celsius, which is a room temperature. Now, as both got the same temperature, it means the equilibrium is achieved. And this is what we call as thermal equilibrium, by the way. Thermal means heat. Now, what do we mean by equilibrium? Equilibrium is a condition at which Heat gained by anything is equal to heat loss. So whatever heat is lost by the cup of tea will be equal to the heat gained by the cup of tea. That's why at 35 degrees Celsius, there will be nothing happen. You won't see anything. And that is what we call as equilibrium condition. In that case, that particular temperature, that particular condition is called as thermal equilibrium. So there are other examples that can be given, but this is the best example that is easily understood, right? Now the next small thing in that case, once you understand with this, now remember that there are different type of energy stores. That doesn't mean that there is a store. Different type of energies, we give them names actually. These are the name of the energies which are being produced, or you can say there are different ways through which these energies are coming from, or the ways through which the energies are coming, and we give them different names. Like, for example, kinetic energy that is coming from a moving object. If object is moving, you will get a kinetic energy. If an object is at certain height with respect to the ground, with respect to the earth, you will have a gravitational energy. Elastic energy. Object have energy in the elastic potential store if they are stretched or squashed or squeezed, right? Magnetic, definitely that energy is everything to do with the magnetic material, right? Then you have electrostatic energy. That energy is basically due to the charges, right? Chemical energy is everything to do with the chemical. So whatever energy is due to the chemical is called as chemical energy. Then nuclear energy. What is that energy? Atomic nuclear release energy, right? And that energy is basically named as a nuclear energy flow. And last but not the least is thermal energy, which is called as a heat energy. So these are all named, we named it store, but definitely these are different types of energy. There are different other energies as well, but there are some names which we have given here. Now, how and what are the ways of transferring energy? There are different ways of transferring energy. You can have a mechanical way, electrical way, heating way, or radiation way. This is the way through which the energy is being transferred from one point to another point, right? So this is the way of transferring energy from one point to another point. Now, what exactly is the thing? Firstly, is called as mechanical. When you say a mechanical energy or the mechanical way of transferring the energy, mechanical is everything to do with the motion. Force acts on it, like pulling, pushing, stretching. So when this thing happens, you're talking about mechanical work. And when mechanical work is being done, that is the way the energy is being transferred from one point to another point in the form of mechanical. Then you will have electrical work. What do we mean by that? It is due to the current, the charge moving through one point to another point within the circuit. Then you have heating. You heat at one point, and then that heat, due to that heating object, transfer to the other end. Then you have heating by radiation. Now, this is the important point. Heating by radiation can be actually given by or can be produced due to electromagnetic waves coming from different object. Electromagnetic waves, we have a topic in the future which we will be discussing. Electromagnetic waves are the waves which do not need medium to travel, like the sunlight which is coming to us on this earth, that is electromagnetic radiations or waves. So energy can be transferred by electromagnetic radiation as well. There are, even on this earth, we have different type of objects which are transmitting electromagnetic waves, and that can be a way of transferring the energy from one point to another point, right? So these are some very basic ways to transfer energy and all that. Now let's talk about some basic energies which we should know, and we got a formula for that. One energy is called as kinetic energy. What is kinetic energy? Kinetic energy is an energy due to the motion of an object. So it means that if an object is moving, the energy that particular object possessed is called as kinetic energy. There is a formula for that. So kinetic energy is equal to 1 by 2 mv square, where m is equal to the mass of an object and v will be equal to the velocity of an object. So it means that if you know these two things, we can easily find out the kinetic energy produced in a body, right? Mass unit, the SI unit of mass is kilograms, and SI unit for velocity is meters per second. Let's have an example that can be done like this. If an object is moving with a velocity of 5 meters per second and have a mass of 50 grams, what will be the kinetic energy produced? Now, this is interesting. How to do this? Mass is 50 grams. So you have to convert that 50 grams into kilograms by dividing it by 1,000. So it will be 0.05 kgs. And the velocity will be 5 meters per second. So kinetic energy will be equal to 1 by 2, 0.05 into 5 square. So what will be the value for that? Let's do the calculation here. 0.05 multiplied by 25 divided by 2. So answer is 0.65625 joules. So this is the answer we have. Kinetic energy. Right? Then we have another energy. We call that energy as gravitational energy. Gravitational potential energy. Now, what is that energy? That gravitational potential energy is due to the height of an object with respect to the Earth. So, if any object is at a certain height with respect to the Earth, you called it a gravitational potential energy, which is GPE. And the formula for this one will be equal to mgh. If you check it out, mg is a weight. So weight into height, where m can be in kilograms. G is acceleration due to gravity. The value is 9.8 meters per second, and h is the height of an object from the Earth. So, what it is? Again, I'm writing a question. If an object has a height of 5 meters from the ground, and has a mass of 25 kgs, what is the potential gravitational potential energy? We can also call it potential energy, by the way, of the object. So simply apply the formula, the data is given. GPE equals to mgh. So mass is 25, G value is 9.8 and 5. That will provide you the answer. 25 multiplied by 9.8 multiplied by 5. So it will be 1225 joules. So this is the gravitational potential energy of an object, right? So these are the different type of energies, and these are different energies which we have discussed. Along with that, it's better to discuss one more thing here, and that is what we called as work. And we will also discuss what will be the difference between the work and energy. Power is different, which we may discuss. We will see to it. If we have time, we will discuss in this lecture. Otherwise, we will be discussing in the next lecture. Work done is what? Very simple. Let's suppose if there is an object and if a person is applying a force and that object displaces a distance t in the direction of force, it means the work is being done. So technically speaking, work done means if the work done is performed only and only if force is applied on an object and a displacement is being performed in the direction of the force. Remember that if displacement is not being performed, work done is not possible, work done is not done. So what is work done equal to? W is equal to force into displacement. Why I'm saying displacement? Because it is in the direction of force. The unit is in Newton meter, but the SI unit is joules. Now, if you see that the unit of work done is Newton meter and the unit of moment, we had done this topic previously, also Newton meter. What is the difference? Both got the same unit, but moment is a vector quantity, has a direction, while work done is a scalar quantity. So work done is a scalar quantity while the moment is a vector quantity. Plus the SI unit for the work done is joules, right? Now, there are a few things which are very, very important to this. If I say an object is here, let's suppose this is a car, it started its journey from the rest. A, the initial velocity is 0 and it travels and it reaches to a velocity, let's suppose, 5 meters per second. The mass is, let's suppose, 2000 kgs. If I ask you, what is the work done? What is the work done? Then work done is stored in a body in the form of change in kinetic energy. So there is another formula you can say, that is work done also equal to change in energy, any energy. In this case, it will be kinetic energy. So technically speaking, in this case, your work done will be equal to 1 by 2. Change in energy, change in the velocity will be 2000, and that will be 5 square. So technically, how much is it in this case? 0.5 multiplied by 2000 multiplied by 25. So it's 25,000. That 25,000 joules is the work done as well. So remember that work done is not just energy transfer, but it's a change in energy transfer. That is easy because it started from 0. So there can be another option, like, because that formula is saying if in this case it can be possible that FD, the force into displacement, is equal to 1 by 2 mv square. There may be a question in which this kind of option you have to apply as well. Plus, there is another option. A car is there and it has some velocity, let's suppose 2 meter per second, and it reaches to the speed of 5 meter per second. The mass is 1000 kgs. What will be the work done? We have already known the formula, delta E is equal to work done. So it will be 1 by 2, 1000 into 5 square minus 1 by 2, 1000 into 2 square. And that will provide you your answer. And what it is? 1000 divided by 2 multiplied by bracket 25 minus 4. That is basically 10500. So this is equal to the work done. Plus, we can have, if how much force is applied, let's suppose if I say, simple question, that for example, 5 Newton force is applied on a box and that box displaces a distance of 6 meters, then what is the work done? W is equal to 5 multiplied by 6, which is equal to 30 joules. Same thing can be happened in case of potential, gravitational potential energy. It can be equal to simple potential energy if the initial potential energy was 0. But if you lift it from a certain height to a certain height, that the change in potential energy can be equal to the work done. Right? So work done can be simple change in the energy. There is one small topic left behind, law of conservation of energy, which means that they say that energy can neither be created. So energy can neither be created nor be destroyed, but can be transferred from one form to another. Now, this is very interesting. What does it mean? I can give you one example. You may understand that, hopefully. Now, what is that example? Very interesting example. The best example is a cup of tea, right? What it is? That cup of tea is here. And it has some temperature, some heat energy. Let's suppose 70 degrees Celsius. That energy, if the surrounding, if a room temperature is 25 degrees Celsius, what is happening? Energy will be transmitted from the cup of tea to the surrounding, as we know that. The question is that energy which is lost by the cup of tea will be gained by the surrounding. So what exactly is happening? Energy is just transmitting. It's not destroyed. It just went into the surrounding. It may be perform some other work. Another example can be, and generally, when in a room you want to turn on the fan, what you would do? You turn on the switch. As soon as you turn on the switch, what will happen? That electric energy converts into kinetic energy. Why? Because fan is rotating, moving, and producing a kinetic energy, produces an air energy, produces an air energy plus heat energy. So what is happening? That electric energy converts into kinetic energy plus heat energy. So technically speaking, that energy, which is input energy, electric energy, transferred into kinetic energy store and heat energy store. So technically speaking, energy neither is consumed, neither destroyed, but it just changes its form. So total input energy must be equal to total output energy. Now, it is not important that is it useful energy or not, but it is important that there is an input energy. Let's suppose if the inputted energy is 50 joules, the output energy must be 50 joules. That is a different game out of which how much energy is useful and how much energy is not useful. There may be some energy useful, some energy not, but some of the energy, but inputted energy must be equal to the outputted energy. That actually leads us to another very small topic. That is what we call a Sankey diagram. And that Sankey diagram related to energy we will be discussing in the next class. Along with that, we will have a power concept, and then we will have different type of energy resources in our course. So I hope you enjoy that video. Hope to see you in the next lecture, which will be based on these all. So thank you very much for watching my video. Bye. Thank you.